Okay, this is lesson 2.2, motion in two directions, and essentially what we're talking about is vectors and vector components. Now when we talk about the components, we're talking a separation of that x and y, separation of x and y pieces of a two-dimensional vector. Of a 2D vector. I like to associate it with that of the old Etch-a-Sketch. Etch-a-Sketches, if you remember, they had the two knobs. One would make the drawing move up and left and right. One would make it move up and down. If you wanted something to move diagonally, you had to use both knobs. The knob that goes horizontal we label as the x-axis, and the knob that has us go up and down we label the y-axis. So if we talk about the separation of a two-dimensional vector, let's say we've got a vector that goes like this, we're going to break it where it had an x piece and a y piece, and we're breaking apart into those two methods. Okay. The polar coordinate method, or rectangular coordinate system as it is called, is a way of measuring angles. Right? It's an angle measurement. Now it works for a full 360 degrees and even beyond, where it moves counterclockwise, from east. So if we had, take a look here, this would be going east is 0 degrees, up to north would be 90 degrees, around 180 degrees would be west, 270 degrees would be south, and so on. It's just a way that we can measure it. The navigator method is also an angle measurement, except this has a little bit of a different twist in the fact that it is in reference to a north, east, south, or west. To a specified direction. And again, that can be north, east, south, or west. So when describing the polar coordinate method, we're going to start facing east, or that x-axis, and turn those degrees counterclockwise. Starting to put clockwise there, but it's counterclockwise. When using that navigator method, what we're looking at is we use the start at the second polar coordinate. Now again, that can be north, east, south, or west, and then turn the indicated degrees towards the first polar direction. Okay, so for example, if we've got 30 degrees north of east, we're starting east and we're turning 30 degrees towards the north. So let's take a look at each of these and try to identify what is used here. Now the first one, if you do not have a northeast, southwest, we're going to assume that it is that polar coordinate method, or the RCS, the rectangular coordinate system. So 3 meters at 0 degrees. So this one here is on the scale is just going to go straight towards the east, 3 meters. 17 meters per second, 245 degrees. Well, we'd start here up to 90, sorry, to 180, and then, well, south would be 270. That's a little bit too far, so it's going to go here around 245 degrees, and that would be 17 meters per second towards the south. Let's choose another color for the third one here. 8 meters per second, 35 degrees north of west. So this is our third one here. And on our coordinate system, we're starting at the west, which would be the negative x direction, and turning 35 degrees towards the north. So it'll look something like that, where this is our vector. Choosing a new color for the fourth one. Choose blue for this one. 2 meters, 65 degrees east of south. Well, this one, we're going to start in that south direction and turn towards the east 65 degrees. So it'll look something like that. Our next one is 7 meters at 98. So we're going to look at this one. We're starting at the 0 and working our way 98 degrees. So our vector would look like this. And our last one, we'll do gray for this one. Our last one is just 65 degrees. Again, 65 degrees starting at east, turning counterclockwise. Now, that's the way that we are describing these different vectors. Now, if we take a look at adding non-collinear vectors, meaning adding vectors in 2 dimensions, and they are not in the same plane, we're going to place the vectors tip to tail. To complete a triangle or a shape with a resultant vector. We can then use trigonometry to find the magnitude represented by the length and the direction of the resultant vector. Okay, so let's take a look at a few examples. The first example here, we're adding 5 meters per second north and 3.25 meters per second at 180 degrees. So I'm going to list this one first simply because it's listed first, and it is going in the north direction 5.0 meters per second. And then we've got this 3.25 meters per second at 180 degrees. Well, that's your RCS method, and it is moving to the west at 180 degrees. So we're placing the vectors tip to tail like this, where we list one and then the tip of one touches the tail of the next and we move on. We can see we've got a resulting triangle from start to finish from adding these two together. Now this happens to make a nice 90-degree angle. So to find the magnitude, we're going to use the Pythagorean theorem. C squared is equal to a squared plus b squared. So c squared is 5 squared plus b squared, 3.25 squared, which means that c squared, typing that in, gets you 35.56 or c is equal to 5.96 meters per second. And so that is the length representing of the magnitude. But we also require a direction. Now, this angle here, starting from the tail of the first vector I drew towards the resultant is how you're going to put that angle in. And so this is the angle we're going to use. And so to find that angle, we're going to use our tangent ratios, opposite over adjacent, which means tan of that angle is equal to the opposite, 3.25 over 5.00, which means when you get a resultant angle of 33.02, or to 2 digits, just 33 degrees. Now this one is in a direction west of north. Another way we could have written that, you may have, for example, done the west first and then the north. You would have wound up with an angle of 57 degrees north of west. A third way we could have written this would have been to say that this started at east and worked their way around, and that would have been a case of 123 degrees on that RCS method. All three directions are acceptable ways of doing it, but just based on the way that I had drawn my diagram, this would have been the answer I would have come up with. Now, again, sometimes you've got vectors with multiple directions, so adding 0.9 kilometers south, 1.2 kilometers east, and 0.35 kilometers north. Well, these two are collinear. They go in the same direction, and if I were just to be adding those together, you would wind up with a 0.9 south and a 0.35 north. That results in a 0.55 south overall. So really we're taking these two and we're going to call that 0.55 south. We then also have a 1.20 east, and so our resultant comes like this. Again, adding them tip to tail, starting from the tail of our first vector we draw to the tip of the last vector we drew. Now, Pythagorean theorem. So c squared is equal to 0.55 squared plus 1.20 squared. And so if you're solving for this, you're going to wind up with a case of a c being 1.32 kilometers. We're going to need to find that angle, which, based on the way I drew this, would have been south and then heading east. Again, using tan, opposite over adjacent. That opposite is 1.20. The adjacent 0.55 means the angle that we get is 65 degrees. And that is east of south. Okay, try adding these three vectors together. Pause the video, give this a try, and then unpause the video, see how you do. If you do have questions, please let me know. Okay, so your final answer should have wound up being 5.4 at an angle of 81 or 81.4 degrees west of north. Now, 8.6 north of west or 171.4 on the RCS are also acceptable ways of expressing that direction. Now, sometimes we're going to have vectors that are not straight in that x and y plane, and we're going to need to break them up into different components. And so we're talking about breaking this vector up into its pieces. Essentially, the x component is going to be associated with whatever is in the right-left direction or the east-west direction, where the y component is usually associated with the up-down or the north-south. So we're basically we draw the vector, and we're going to make a right angle triangle to find the two sides. So here we've got 12 meters at 30 degrees north of west. So starting at west, turning 30 degrees towards the north would look something like this. And it's 12.0 meters long. And so this has an x piece and a y piece. Really, ultimately, once you've drawn this vector, you're just actually looking for the other two sides using trigonometry. This x can be found using, is he adjacent to that angle? And so we're going to use cosine. Cosine of an angle, remember, is adjacent over hypotenuse. That adjacent I'm going to replace with x because it's the x component we're looking for, over 12, or 12 times cos 30 is equal to x. What you find is that component is 10.4 meters in length, and that component is, of course, a west component. To find the y is opposite of that angle, so you're going to be using sine, opposite over hypotenuse. So sine 30 is equal to, I'm going to replace that with y over 12, where 12 sine 30 is equal to that y. What you find is that is 6 meters for the y component, and that is, of course, a north component. Okay, let's try this next one. We're breaking 100 kilometers an hour, 40 degrees south of west. 40 degrees south of west would look something like this. It's 100 kilometers per hour. And again, we're just breaking this off into its little x and y components. So that x component is, again, adjacent. So using cosine of the angle is adjacent over hypotenuse. Cosine 40, x over 100. 100 cos 40 is equal to x. So that component is 76.6 kilometers, and again a west direction because it was a west component. To find that y, I'm going to use sine because y is opposite of the 40-degree angle based on the way that we drew it. Well, actually more based on the way it was written. That y component over 100, or 100 sine 40 is equal to that y component. You find that y component is going to be equal to 64.3 kilometers, and that's in a south direction. Okay, give this next one a try, and let me know how you do. Okay, you should have found that west component of 4.2 meters per second, and that south component being 9.1 meters per second. Now, one of the things you may or may not have noticed is that because each time I always used my main reference as being the x direction, cosine wound up finding the x, and sine always found the y. However, if you wind up using the y-axis as your basis of comparison, for example, if we would have used 25 degrees and used this angle here, those actually would have been flipped. So it's always helpful to draw the diagram, and so you never make a mistake from the pieces coming together. Now if we add the components together, really we're going to break everything into components. We're going to add the vectors collinearly and combine the two results. Right? So all the skills we've had have led us up to these sort of examples. All right, so let's take a look. We've got 20 meters north and 15 meters, 25 degrees east of south. Well, we're going to break this apart. This first vector is really easy because it's already just 20 meters north. The second one has both an x and y component, so we're going to need to break it down. 15 meters, 25 degrees east of south. Well, east of south would look like this, 25 degrees. We're coming up like this, 15 meters. Now, because this is being drawn with the south as kind of our main reference point, we'll notice that the x and y cosine sine association actually flips. So to find the x component, we're going to be using sine. Sine 25 is equal to x over the hypotenuse, or 15 sine 25, and that component is 6.339 meters. Finding that y component, we're going to be using cosine y over 15, or 15 cos 25, and that component is 13.59 meters. Okay, so we've got everything broken up. This was the x component, and so it is moving east, that's south, and so essentially we're going to need to add all the y's together and add all the x's together, although there's only one x. So adding these y's together results in 20 meters north and 13.59 meters south. That means that the y total is going to be 20 plus negative 13.59. That gets us a total of positive 6.41 meters, or 6.41 meters north. That total x, well, there's only one of them, so it's nice and easy, of 6.339 meters. So we're going to add 6.41, 6.339, adding tip to tail again, coming up like this, and now we're going to use trig to find the total resultant. 6.339 squared plus 6.41 squared. We wind up with the resultant of 9.0 to 2 digits. Our angle here, using tan, opposite over adjacent, 6.339 over 6.41. That angle is 45 degrees to 2 digits, which makes sense in terms of these numbers are very, very close to one another. But the way we drew that is east of north. 9 meters, 45 degrees east of north. Let's take a look at another example here. We've got components, but this time we're going to have to break both of them up. 15 kilometers at 220. 220 is coming around here. That's essentially 40 degrees south of east. I'm going to need to break that one apart because it came 220 this way. And the last one, 335, well, that is almost a full circle. Not quite, and so I'm going to just call this 25 degrees because in actuality it indicated 335 this way. And we're going to need to find the components of this one too. All right, so we're looking for those xy components. To find the x component here, that's going to be, oh, I should probably put in the values here just so we got. So this will be 15 cos 40 to get the x component, and 15 cos 40 is 11.49 for that x component, and 15 sine 40 gets you 9.64 meters south and west. My 4 there is looking very much like a 9, so I'm just going to fix that so it looks like a 4. Sorry, I mixed that up there with those ones. My apologies for that. To find the x component, it's 25 cos 25 will get us the x component. That x component is running 22.6 east. To find the y component is 25 sine 25, and that is 10.6, and that's running south. So adding the east and west components together, the x components, the x total, that comes from an 11.49 west, so we'll put that negative, plus 22.6 east, so we'll call it positive. That total x is 11.16, keeping our calculator answer in an east direction. We know that because it's positive. The y totals are adding the two souths, and so it's going to be negative 9.69 plus negative 10.6 for a total of negative 20.2. That negative just indicating south. So runs like this, 20.2, runs like this, 11.16. We're looking for this resultant. And now we, again, Pythagorean theorem. We're using c squared is equal to a squared plus b squared, 20.2 squared plus 11.16 squared. That gets you a result of 23.1 kilometers. And the angle using tan gets you an angle of 29 degrees. Now the way that was drawn is here. To keep it in the RCS method, because we're putting the RCS method because it's going a little bit beyond south, that's actually 299 degrees on the RCS method, 299. Okay, give this last one a try and let me know how you do. So breaking apart that vector into its components, adding all the x's and all the y's together to make your new triangle, using Pythagorean theorem to find the magnitude, and using the tangent ratio to find the angle, should get you 137 meters and 10.7 degrees south of east. Thanks for watching.